10 years. So this is basically a compilation of various techniques that we've applied to try to handle a very messy source separation problem. We have lots of collaborators doing carbon at NASA Ames Research Center. One of my students, Joshua Chewinski, has worked on this for a while. He's now doing other things. Dennis Genshaw was here in the audience, was my postdoc at the time, and he's now at CCNY working with Bill Wassow. Dennis would never say this, but I can say it. He's looking for a job. He's very good and very smart, and if you need somebody, he's over there. Haley Manu is also one of my students. She'd worked on this for a while. She's now doing other things. And Nathan, one of my students, is now at the University of Texas, Dallas, and FITC, who's now doing economics in my lab as well. So this has been going on for a long time. People have spread out a bit. Here's a lovely picture of Orion. Of course, we have to show some nice pictures here. But I want to give you an idea of what we're looking at. If you zoom in a lot, you can see the Orion Nebula. And if you zoom in even more, you see this region here. It's called the Orion Bar. This is a cloud vein that's being illuminated by a very hot star. We get a lot of ultraviolet light. So there's complex molecules in here that are being excited and re-emitting in the infrared. This is what the emission looks like. This is over 3 to 20 microns. You can see there's a lot of spectral lines. There's some atomic lines here, which are the very narrow ones, but there's a lot of very broad lines here, which is coming from this UV lit dust. Back in the 1990s, people weren't sure what this is, and at this point we now know that these are polycyclic aromatic hydrocarbons. So stars, as they go through their carbon nitrogen oxygen cycle, are pumping out these elements that then go into the interstellar medium and right away form organic molecules. So we'd like to know what precisely which organic molecules are present. Given a cloud at a certain temperature with certain densities, what species do you actually create? Which are easy to create, which are hard to create, that's just not known. Some of the other spectra here, this is from M17. You can see similar peaks in similar regions, so the same thing's going on. This is the Swan Nebula, and we're actually going to look at this region right there. If you zoom in, there's the cloud bank there where you have this dust. The last one is NGC 2023, which is this cloud here that's being illuminated by this young hot star as well. So these chemicals are all over the place, and we'd be very interested in finding out what's present. This is what they look like. They're made of little benzene rings that kind of attach together to form these chicken wire type structures. So some of these are familiar. Naphthalene is what you have in your mothballs. So these are very common organic molecules. The group at NASA Ames Research Center has been working very hard for the last two decades maybe to try to determine the spectra of these molecules. They're very hard to isolate. You try to get one species together in a jar, collected in a jar, but they collide with each other and stick together, so immediately they diversify. So it's very tricky in the lab to be able to get an isolated species. So this is how the quantum computing group got involved. The chemists were working to isolate spectra while they were trying to model them using quantum mechanics. And together they've been able to estimate with a good deal of accuracy what the spectra for about 1,000 PA species look like. So each of these has some unique features. You can see that some of these are shared. These are coming from vibrational modes, so these molecules can be stretched and twisted and things like this. So they have very similar spectral characteristics, but not identical. So why are these things interesting? About 10 to 20% of all the carbon atoms in the interstellar medium are PA molecules. They're found in almost every cosmic environment, and they could be used to characterize the conditions of the interstellar medium if we understood how they form these in various locations. And they appear to be very important molecules on the pathway to life. So the difficulty is that no astrophysical source shows the unique signature of any identifiable known PA. these things always come in mixtures of probably thousands of different types of molecules. This is really a horrible problem, and I have to say there have been times when I've questioned my sanity when I took it on. It gets worse because there's a lot of things going on out there. Here's your telescope, you're looking along some line of sight, and you're looking through several different cloud banks, which could have, in the intrasolar medium, which could be at different temperatures. So you have black body radiation, you have absorption going on, you have emission, you have all sorts of awful things. And these all combine to give you these very rich complex spectra here that we'd like to understand. So here, these molecules are only contributing to some of the features in the spectrum. There's a lot of other things going on. You can see there's this general rise that goes up. This is due to the Planck black body spectrum that's buried under here. So there's some background, what we would call background, if that's what you're not interested in studying. That's some of the features we'd like to remove are what we call background features, which are actually important features for other people. So here's one of the models we started with. We imagine that the spectrum consists of some pause. They have a certain concentration. We put in this on-off parameter that can be 1 or 0 to indicate presence or non-presence. This is a very handy thing to do if you aren't sure whether if you want to actually estimate when something's present or not, model it, right? And so you can get a probability for whether the pause is present, independent of the probability for what its concentration is if it were present. We then have the possibility of there being several overlapping Planck black body radiators in the field of view. And then there's all these other features that we have absolutely no idea what they are, from dust and various other things going on. And we tried using some Gaussians just to try to model these. So some of these are actually, like these types of features here, it's not clear whether this is due to a bunch of pause spectrum piling up and giving you this lump in the spectrum, or whether there's something else going on underneath. And this also makes the problem especially horrible. So here's our Planck black body radiators. This is the expression for the Planck black body. So this is a parameterized model. That's very nice to handle. That's not so bad. And this is the kind of throw up your hands, I don't know what to do with this part of the spectrum term. So these pause pose unique difficulties. Most source separation problems consist of multiple mixtures and a handful of unknown sources with unknown contributions. This isn't just a handful, we're talking about thousands here, and probably many more that we haven't tried modeling. There are, how do you tell which ones are present? How do you deal with these large numbers? And those are some interesting challenges. The database at NASA Ames now exists that I don't know if it's public or not. I haven't looked for a while. I got the data directly from them, but this is the portal, and you can get pause spectrum for about around 1,000 different species. So one of the things we started to first was, well, let's try to handle the Planck black body radiation. Let's get rid of this background signal. And this was an interesting lesson. So here is the Orion bar, and here is our estimate of the Planck black body radiation. And very nice. We found that there's one black body radiator at a temperature of 61.043 plus or minus 0.004 Kelvin. Very nice precision. Wonderful. But then there's a 36.3% chance there's another one around 18.8 Kelvin. This is all fine and good, except there's a problem, and that's the problem there. Our model is going above the actually measured flux, which means if we subtract off the background, we now have negative flux, right? So that just says that this is not a very good model. Well, why is this happening? Well, it's because we have a nice Gaussian likelihood, right? That's nice and symmetric, and so the inference algorithm doesn't care whether we're above the curve or below the curve, and it gives us the best fit, right? So this is the best fit, assuming that you can actually be above the curve. But you can't be above the curve, because we can't have negative photons hitting our detector. So there's a problem here. So I'll address that problem a little later. I'll show you what we did with estimating pause. We started out with synthetic mixtures, and of course you do the simplest thing first. We tried linear least squares, fits, and this uses the Nelder-Mead simplex algorithm that basically crawls up using a simplex to find the peak in this high dimensional space, 187 dimensional space.
Why did you only use 187?
Dwayne picked a random number and sent us the data without us knowing what he used. So
Okay.
we actually tried many other numbers, but this is one that particularly shows how your algorithm can make a difference as well. So here you can see that these are the true concentrations or weights in the synthetic mixture. Here's the inferred weights, and yeah, we're along the line, but we're off quite a bit on a lot of these. So this is basically a gradient descent type algorithm that's not going to really explore the space. If you use something like even something as simple as Metropolis, Hastings, Markov chain, Monte Carlo, that actually takes its time and explores the space carefully, you can see you can do a lot better. So this is actually the same data set. You find that if you run this multiple times with different starting conditions, you get different answers. That's one good way to find out that you actually have multiple peaks in the space, and you need to be very careful. So we are able to unmix a large number of PAWs. I don't think I actually put a picture of what the mixture looks like, but they pile up quite a bit, and it's very hard to disentangle it with your eyes. But that's in the noise-free case. You start introducing noise, and that adds a whole new element of difficulty. We found when with even a small amount of noise, unless it's a very, very strong PAW signature, it's very hard to be able to identify that PAW species. It's just too difficult. You just don't have enough information. So one of the things we wanted to do is to handle this background problem. Here's another spectrum. I didn't write down which one this was from. This could be from the Starburst galaxy. Yeah, Tom.
Are you looking at like a particular instrument in mind? Is the limitation with the simple method with just a little bit of noise to finite spectral resolution, or is it something more fundamental?
Well, we were developing our algorithms in general, and then taking into account, Dwayne Carbon was taking into account the specific instrument parameters when he was making our synthetic mixtures to play with, basically. Yeah, if you put that information into the problem, and it of course improves things, but even with the synthetic mixtures, even adding noise to the PAWs, unless you have a very strong a single PAW signature, or a very clean window somewhere, it becomes very difficult to identify them. So what do you do with this background? I mean, there's some plain black body radiation here, that's fine, and we saw some of the difficulties there. What people had been doing previous to our getting involved was to basically fit curves to this by hand and just subtract off the background. Guessing, right? I mean, what else are you going to do? We have no idea what some of these bumps are. Is this from PAW spectra? Is it from dust? Who knows? So you may draw your line under it and include that in your as part of your data, or you might try to rule some of that out and include this peak. People would try different things. So we did some experiments to.
What do they do with the negative values? What do they do with the negative values where they can't fit on the top? Like you just showed.
When you get the.
What did they do about that? They just.
I don't actually know.
Okay.
Fitting this by hand is very difficult. It's very hairy, right? I mean, you're already making lots and lots of assumptions.
Yeah, exactly.
So one of the things that Brian Nathan, one of my students, did is he did a short study to see how different your PAW estimates are in its synthetic mixtures if you subtract the background in different ways. And of course, it's very different. We knew that would be the case, but there were some people who claimed that, well, it can't be that much different. So this was an issue that actually.
Well, isn't part of the problem that PAWs also can be very broad, right? So they can cover 10 microns.
Oh yeah, the spectra.
Yeah.
It depends on. Yeah, the spectral lines can be.
So yeah,
spread
it
out.
makes total sense.
That's right.
If you
So we just developed an algorithm that actually is pretty nice to try to handle this. Basically, it's based on a spline model, so here's just a simple spline approximation of a sine curve, and the little circles on here aren't showing up. But this algorithm basically models the spectrum with a spline curve, so you have a finite set of spline knots, and we use a Gaussian that is, or a piecewise Gaussian, so it has a wider sigma on one side than it does the other. Basically, they differ by about 10 to the 6th, 1 10 to the 6th. I told you a million times, do not go above that line, you know, so put a million down there. And it's strong enough to make sure that you don't go above this line. There's a huge penalty, basically, for introducing a negative flux, right, in your signal. So we have this very simple likelihood function. We also tried putting in, we've done various things. Like I said, this has been going on for a long time. A smoothness prior, so you have a prior probability, which is basically a Gaussian on the integral of the second derivative. So you can put in, this is the free parameter here, you can basically say how smooth you want this function to be. So you can put this prior in, and this will help influence the spline fits. So here's one of the results on some synthetic data. And here you can actually see this is a synthetic sum of pos, so you can see how they actually pile up. This is actually, I think, from 187 pos as well, that same data set. And our algorithm then fits the background, basically trying to estimate what this background looked like. So when we constructed this, we actually put in some Gaussian curves as the background. This is actually, there's actually a Gaussian here, but it's actually a much smaller width. And here we had a very strong prior on smoothness, so you can see that there's some ability to fudge and play with this again. And of course, once you subtract off the background, you can then recover your signal. This is the idea. Here's one of the possible backgrounds that you can have for the M82 starburst galaxy. So you can see that we're trying to model some of these larger features here. This bump here, part of it got modeled, and then the idea is that these small peaks on top are probably due to the pos. How could the whole thing be due to the pos? Yeah, good. Who knows? This is an exceptionally hard problem. You don't actually know. Here's another picture just to show you one of our fits on the Orion bar, so you can see how you can model the background this way. It doesn't go above the curve, which is a very nice feature. I'll give a quick live demo so you can see this work. All right, so this is actually going to just fit a sine wave. We've got a sine wave riding on top of very low frequency sine wave. The low frequency sine wave is the background, and there's a high frequency sine wave on top, which is our data. That we're interested in, the relevant data. This algorithm is actually using the smoothness prior, so we're using this piecewise Gaussian likelihood along with the smoothness prior, and it's very fast. I mean, I don't even have, I'm showing you the iterations, so if I don't plot it, it's much faster. Just to give you some idea of what we're doing. I know this is extremely technical. So when you're finished running the algorithm, based on the smoothness prior that you put in, you have a fit for the background, and then you can extract your signal from that. So it's better than doing it by hand.
What was the input? The first peak in the input was like that, or they're supposed to be all the same? The input signal.
They're supposed to be all the same. Yeah, it's a sine wave. They're supposed to be all the same. The problem with splines is that you've got a loose end, right? So it's going to behave polynomially at the end.
So you know to ignore the.
Yeah. Exactly. I'm sorry?
Is it noiseless?
Is it what?
Is noise dedicated noiseless?
Oh, in this case it's noiseless. But even if you had noise there, it would still would still fit this nice curve. It would still do that. So you can also do this without a smoothness prior. Here actually I have one of the ways to do this. This uses a smaller number of knots. So one of the ways to handle this, let's say that this peak here you knew was actually important, was part of the background and you didn't want to include it, you could actually put extra knots in here and actually model that peak. So you have some freedom to play around with this. I don't know, it's like having freedom in data analysis. Some people like having freedom in data analysis too, but I actually don't prefer that. But here, because you have no idea what this background is in the first place and how much of it is actually the signal you're interested or signal that you want to get rid of, you can only decide. So that's basically the situation. Let's see here. Oh, I can just pull it up here. Excellent. All right, that went pretty quickly. Yeah, so this was funded by AISR back in 2005 for a few years, and we still play around with the problem a little bit. We've also moved on to other things. So. Okay, thanks.
So when you model the very complex spectra with your library of 187 or some plots, are those drawn from your library and it finds the ones that work best?
Oh, yeah, I maybe didn't.
You pre-select?
Well, when we try this with the real spectrum, I didn't go this far. It's impossible to actually do the estimates. The algorithms don't converge. If you look at these, if we go back here, the spectrum's still just far too complicated. We don't know what half of these little lumps are down here, and things like this can really accommodate lots of different combinations of cause. So your uncertainties are just way too huge.
Okay. I guess I misunderstood. So you can't, for example, tell a astrochemist what are the causes that are making that bump?
No, not yet. No. Yeah, we weren't successful to actually solve the problem. There's just not enough information about, because there's lots of other sources of dust. Dust is doing things, and none of this is in the model. Presumably, if you knew more about what was going on and you could incorporate that into the model, you could do better. The freeform mixture of Gaussians model, it's not providing any information to the problem, so you're not able to pull out a solution. Yeah.
For the background estimating problem, there are big lobes. Those are easy to visualize. And then there's these little or medium-sized features, like you pointed out. Let's say like micron wire.
Right.
And suppose, say, by mistake, you subtracted this smallish feature. What exactly are the consequences of taking out that?
That's a very good question. The consequences are that any pause, this is something we did explore in some detail. The problem is that the consequences are that any pause that do contribute spectral energy in that region, you basically reduce their overall energy by a large amount, right? You've put a huge constraint. So let's say these were all pause, right? But you didn't realize that. So you subtracted out basically half of the spectral energy there now. So now every PA species that has spectral energy in that region, you've now basically told your inference algorithm it can't possibly have a concentration more than this, because if it did, it would you would have more spectral energy there. So now you've limited the potential concentrations of a particular subclass of PAS. And so you now are going to get, your inferences are going to be wrong, you're going to be biased. In addition, you're going to now have spectral peaks out here that can't be explained by by the pause that you've reduced because you've reduced their spectral energy there, you now have additional spectral energy here that you can't model. So you've got this incommensurate situation where it can't be, if PA had a peak here of 10 and was supposed to have a peak here of 20, but you took out 10 units here, now this can't be PA with the spectral energy of 10. And so you end up not modeling this area well either. And if you have any if you have any broadening of the spectral lines due to it isn't really going to happen too much due to thermal broadening, but it could be because of the instrument the effect of the instrumentation on the spectrum. So if you have some instrumentation broadening here, then you might be able to fit a different PA to this peak, this unfit peak. Part of the spectral energy here that's now not being fit because you reduced this here. So you're going to basically decrease the concentration of some of the PAs that were there, and you potentially may increase the concentration of PAs that aren't there. So it can do both horrible things to you. Basically, and because you don't know what's there and what's not, it's basically just going to reshuffle the PA concentrations either up or down, and you have no idea which way they've gone. So, that's really why it's a horrible problem, because we know that not all of this is due to PAs, but we just don't know how much is due to PAs and how much isn't. So it's really, in some sense, unsolvable until we have better models for how dust behaves and what might be present.
I know that this is that do only small PAs be bigger or be radiate in unit in the bound?
Well, that's something that would have been really nice to know, right? What is it? Is it more probable to create small PAs, or is it turn out to be more probable to create big PAs, or is there some happy medium where you're going to get PAs of size n, right, with some variance? That's one of the things we really did want to find out. If you have that information, you can use it as a prior on the PAs to put a prior on what PAs are present. But the fact is that nobody really knows. We've only recently discovered that they are PAs, and nobody really knows what proportions they get created and whether that has any relationship to their mass or size. Questions?
I think you're right. It's a really, really hard problem. These
horrible.
PAs are really poorly understood. There's very few lab observations. There's almost no funding for this stuff. It's extremely important, but nobody seems to care.
That's right. Actually, I submitted this abstract to the statistical the SPS meeting for statistical signal processing in 2007. And of course, the reviewer, you get reviewer comments for your abstract, and there were 3 reviewers. 2 were very nice. The third one was, this can't possibly be a solvable problem, and he rejected it because it was not solvable. And my response was,
You're right.
Well, let's not try. Just give up, right? I knew this would be a really hard problem, but then let's see what we can do with it. And now we know where the weak points are, and some algorithms came out of this that are useful in other problems. So.
I would say another problem is that these lab PAs, some of them are highly toxic and highly carcinogenous. So you're basically forbidden by law to mess around with some of these things. You have to be extremely careful with them. So it's extremely expensive to deal with these things in the lab to measure the spectrum of these different species. People want to do it, but there's very little funding, and it's dangerous.
I think what Louis Alamandola's team had to do is they took tar paper and they boiled the tar to get the volatiles out, basically, and then they isolated the PAs from the volatiles. They couldn't get it anywhere else. These things are really horrible. So, yeah, Tom, you have a question?
Comment and question. Comment. I don't do it under astronomy, but in the building full of reviews. Some of the people who build instruments on Spitzer in my building, and they've given up on this. They recognize it as scientifically important, but they've given up on it. However, they do are speculating that it will become more feasible with JWST. So I think there's hope. I mean, I think certainly that community is interested in having people work on the data analysis for these problems in light of JWST. So
Right.
But why do they think JWST and not Herschel? Because Herschel goes much farther out into the infrared.
That's a good question. I think it's just a matter of the size of the telescope and signal to noise. I don't know.
Okay.
And then the question was, did you ever try joint fitting of the background and the line?
Yeah, we tried that too. Yeah, it's equally difficult. Well, actually, it's
If
harder.
one of them doesn't work, the others won't, but I just wondered.
It's harder.
I mean, can you get any handle on the kind of ambiguity you were just talking about where your background model could be fitting some of the paths, but if you were to fit them jointly in a framework that let you take into account, let you somehow report model uncertainty, not just the best model, then can you have an algorithm that at least tells you don't know, as opposed to reporting a batch?
Yeah, well, we did do that. We had estimates of the uncertainties, and that worked very nicely in the synthetic mixtures, but the real mixtures, the uncertainties are just huge. There are some that you can nail down. I mean, this is an atomic line here. These are atomic lines, and those you can nail down. And when they're related to each other, it gives you an idea of how the background here compares to the background there. So you can get some information from the atomic lines, but they're just they're so narrow. So you're just getting a few points on this curve, so it's still not enough information.